Hello everyone, my name is Shahriar Rumidipto. I'll be presenting our paper Algorithm-Based Pipeline for Reliable and Intent-Preserving Code Translation with LLMs. This paper was accepted at the 34th IEEE ACM International Conference on Program Comprehension ICPC 2026. To start with, our main motivation is reliability in code translation. We know code translation is useful for migration, reuse, and cross-language development. But in many cases, we still use LLM-based translation as a one-step black box process. In practice, we do not just need translated code, we need code that preserves the original intent and actually works. We assume that adding a short algorithm step before code generation can help, but we still need to check how it affects the correctness and error behavior of the translated program. In this work, we argue that one-shot translation is brittle because small mistakes in parsing, typing, bounds, or output format can break the final solution. So we test a more structured workflow where the model first creates an algorithmic plan and then generates the final code from that algorithm. This figure shows our motivating example. In the source Java code, we first read the sizes and then fill two lists from the input. In the Python direct translation, the input pattern changes. It builds one long list, then slices it, and which causes an index error. On the right side, the model first generates a short algorithm that keeps the original input behavior clear. Then the final Python code follows that algorithm, matches the Java logic, and runs without any error. This example shows that even a small change in input handling can break a program, and the algorithm step can help prevent that. Our paper is organized around three research questions. The first question asks whether the algorithm step improves the translation accuracy or not. The second question examines what kinds of failures appear in each pipeline. And the third question asks whether the algorithm-based pipeline actually reduces those translation failures or not. This slide shows the core methodological difference between our two pipelines. In the direct pipeline, we give the model the source code and it generates the target code in a single step. Whereas in the algorithm-based pipeline, we first ask the model to produce a language-neutral algorithm and then we use that algorithm to generate the target code. The key point is what this intermediate algorithm captures here. It forces the model to state the input-output behavior, data structures, numerical rules, loop bounds, and output format before writing the code. As we keep the prompts fixed across models and datasets, we can isolate the effect of this planning step. Our evaluation setup is strict and practical. In the study, we used 2 datasets, 2 translation directions, and 5 strong LLMs. Most importantly, we make the comparison paired so both pipelines use the same programs and the same test suites. This makes the results easier to trust. Because the datasets already provide validated tests and clean input-output behavior, we can automate the full workflow. For every model, dataset, direction, and pipeline combination, we compile the generated program, run it, and execute the provided tests for all the translated programs. And we count a translation as correct only if it passes all three stages: the compilation stage, the runtime stage, and the passing of all the test cases. So we are not just measuring the code that looks plausible, we are measuring code that is actually runnable and functionally correct. Now we come to the main result. Across all runs, we see the micro-average accuracy increase from 67.7% in the direct pipeline to 78.5% in the algorithm-based pipeline. That gives us a gain of 10.8 percentage points. This improvement is broad rather than isolated, as most combinations perform better in the algorithm-based pipeline and the largest gains appear for Llama 4 Maverick and DeepSeek R1 model. We also find that the algorithm step helps most when the task is sensitive to typing, parsing, loop bounds, and input-output contracts. In short, we show that the algorithm step improves the reliability of a translated program. Our paper does more than just showing improvement in accuracy. It also explains why translations fail. To do that, we built one shared taxonomy that works for both translation directions. We grouped the runtime failures into 6 categories, which is RE1 to RE6, and the compile time failures into 7 categories, which is CE1 to CE7. Among these, two results stand out. First, we find that the runtime failures are mainly caused by parsing and type conversion problems. Second, we find that compile time failures are mostly caused by structural and declaration issues, especially when we translate into Java. So the main weaknesses are not random. They cluster around the input-output handling, typing, and target language structure. This slide answers the most practical question, which is where the algorithm step helps. We see the strongest improvements in setup and structure sensitive failures. Dependency and entry point issues drop sharply. Lexical and token errors disappear completely. And the incomplete constructs and structural declaration problems also decrease by large margins. These reductions matter because they remove many avoidable compile breaks and runtime crashes. At the same time, not every problem goes away. Missing state issues and type or overload resolution problems can still remain or even increase, so we still need tighter semantic checks. Our final message is practical. We suggest that teams should treat the algorithm as a checklist before code generation. It should make input handling, data structures, numerical rules, loop bounds, termination of program, and output format explicit. In engineering terms, we find that translation works better as a small deterministic pipeline with validation than as a single model call. At the same time, we recognize that the study has clear limits. We focus only on Python and Java and we assign the taxonomy manually, although the agreement is high. A natural next step is to expand the study to more language pairs and to develop machine checkable algorithms or plans. And that is all. Thank you so much. If you have any further questions, suggestions, or any concerns, you can contact us through our emails. Thank you so much.